In 1997, the Thrust SSC became the first car to beat the speed of sound by setting a new land speed record of 763 miles per hour, or 1.02 Mach to be exact. Almost 2 decades later, the same group of people is trying to smash that record once again with a new supersonic car called the Bloodhound SSC. Today we are going to take a look at some of the key components that makes the Bloodhound SSC so fast and so special. The Bloodhound SSC looks more like a supersonic jet fighter than a car, and that's because it has been designed with only one purpose in mind: to reach 1000 miles per hour barrier. For that, the car has to be narrow as possible, streamlined as possible, and should have less aerodynamic drag as possible. The Bloodhound SSC has an hybrid construction, which means the forward half of the car is made from carbon fiber, and the rear section is of metallic fabrication. The front section of the car is a Formula 1 style carbon fiber tub, providing the driver with a very safe and rigid cell. It also places the main jet intake above the cockpit. The rear section of the car is a metallic fabrication which is split along its center line. The upper chassis is of rib and stringer type, which is a typical aerospace construction. The ribs are made from aluminum billet, and the stringers are fabricated in titanium. This part of the chassis mounts the jet engine. The lower part of the chassis is a series of aluminum frames and bulkheads, which are made from steel. This structure mounts the auxiliary power unit, jet fuel tank, and the rocket system. The Bloodhound SSC won't be having any pneumatic tires, and that's because it is nearly impossible to produce a tire that can handle the extreme G-forces and the centrifugal forces during the high-speed run. At 1000 miles an hour, the wheels of the Bloodhound SSC will be rotating at 10,200 rpm. Keep in mind that the maximum speed at which a F1 wheel can turn is only 2500 rpm. The wheels of the Bloodhound SSC will be manufactured by Autofox in Germany, and it will be made from an alloy called 7037 aluminum, which is mainly used in aerospace application. The cast aluminum alloy block will be forged into shape using a 3600-ton hand forging press. One of the honing challenges for this program was putting the massive 7-ton supersonic car to rest before the track runs out. Most of the braking duties will be handled by massive air brakes like active aerodynamics and parachute, etc. But a wheel brake is necessary to ensure that the car stops within the desired distance. But these brakes will be activated only from 160 miles per hour to downwards. Initially they used carbon rotors, but it didn't survive the spin test. Then they experimented on steel, and surprisingly it not only survived a single run but lasted for multiple runs. During the braking, these discs will reach temperature up to 850 degrees Celsius. Since the car is very narrow to reduce drag, the calipers have to be built into the front upright. The rear wheels will not have any brakes in them. The brakes will be manufactured by AP Racing. While driving in supersonic speed, even a false minor steer correction will have catastrophic effect. Also, a small bump can have enormous feedback in the steering. So the primary objective for the designers and engineers, which might sound a little bit weird, is to minimize the steering response as low as possible, at the same time providing a greater control over the car. For this purpose, they used worm and roll steering system instead of a rack and pinion. The steering has a ratio of 30:1, which means you have to input 30-degree turn in the steering to get a 1-degree turn in the wheel, and that can be altered all the way up to 90:1. Both the front and rear wheel uses the Formula 1 type double wishbone setup, since it gives the best suspension stiffness. This in turn prevents the wheels from flexing off the line. The front track is 1 meter and the rear track is 2.3 meter wide, which gives the best compromise between vehicle lateral stability and aerodynamic drag. To begin with, the Bloodhound SSC will have 3 different forms of IC engines. First one is a jet engine called Eurojet EJ200. The second one will be a hybrid rocket engine, and the third one is a Jaguar supercharged 5-liter V8 engine. This jet engine is the initial power source of Bloodhound SSC. This engine is widely used in Eurofighter Typhoon fighter jet. It is capable of producing 16,000 pounds of thrust and an additional 4,000 pounds of thrust with reheating. The rocket used in Bloodhound SSC is hybrid one, since it is safe compared to other type of rockets like solid rocket and liquid rocket. The solid fuel, which is hydroxyl terminate polybutadiene, a synthetic rubber compound, will be placed inside the rocket. The oxidizer, high-test peroxide, will be placed in a separate tank, and it will be supplied to the rocket with the help of an oxidizer pump through a silver-plated catalyst in order to vaporize the oxidizer before entering to the rocket for combustion. The rocket will be activated once the car reaches 400 miles per hour. The 5-liter supercharged Jaguar engine is an auxiliary power unit, which means it will only be used to drive an oxidizer pump. A 550 bhp engine just to drive an oxidizer pump. Before you say anything, let me just point this out. The pump will have to deliver 800 liters of fuel in just 20 seconds. That's 40 liters per second. That pump definitely needs some serious power. The design of the oxidizer pump has been borrowed from Stentor rocket, which is used in Blue Steel cruise missile. Since there was no drawing available, the design has been re-engineered. The pump has a 5-blade impeller and 3-blade axial inducer. If you find this video interesting, please be sure to subscribe, like and comment.